This brownie is so good. I wonder how it was made.
Through the elementary steps that we're going to talk about in this video.
You ready? Let's go!
This week we're going to zoom in on Chapter 7 and look at an overview of the most common elementary steps. These steps combine to make up every reaction in everyday life. And the four most important things we need to remember as we go through each of these elementary steps is that nature avoids charge separation, just like Dr. Cabot always says. Electrons move from electron-rich areas to electron-poor areas. Charge stability is favored over bond energy, and every reaction requires a driving force and a pathway.
Okay, this is a biomolecular nucleophilic substitution step, abbreviated SN2. And in this step, you're going to take a substrate and you're going to attach a nucleophile to it while making the leaving group leave. So in this case, we have the two electrons from the hydroxide coming over and forming a bond with the carbon, while simultaneously the electrons from that bond create a complete octet for the chloride. And so here you can see it has a negative charge, but leaving groups usually are conjugate bases of strong acids, so it's very stable having that negative charge.
Two of the most common elementary steps is the coordination step and the heterolysis step, where one is bond forming and the other one is bond breaking. In the coordination step, a single covalent bond is formed between an electron-rich molecule and an electron-poor molecule, creating a single molecule here. In the heterolysis step, it is the reverse reaction, where a single covalent bond is broken and both of those electrons end up on one of the originally involved atoms, where it ends up with an electron-poor and an electron-rich molecule.
Okay, next we're going to talk about the biomolecular elimination, or E2 steps. In this kind of elementary step, we're going to have a substrate that's going to react with a strong base in order to give us a more stable set of products. So in this example that we have a cyclohexane that is connected to a hydrogen and bromine, and then we have our strong base here, which is OH with a negative charge. So electrons always move from electron-rich to electron-poor. So our negatively charged strong base is going to move its electrons over to our hydrogen, and then the bond between the hydrogen and the cyclohexane is going to move over between these two carbons, creating a new double bond, and then the electrons from this single bond are going to move over to our bromine, creating a negatively charged bromine ion. So our substrate has to have two important things. It has to have a hydrogen and a leaving group, which is in this case bromine, connected to adjacent carbons, and both will be eliminated through this elimination step. And these are really important because they introduce carbon-carbon multiple bonds into our reactions.
Alright, so I'm going to be talking about nucleophilic addition and elimination. We've seen already that a nucleophile is an electron-rich molecule, and with nucleophilic addition, the nucleophile can bond to an atom that is part of the polar pi bond. So we see here water, its oxygen has two lone pairs, and these electrons will bond with this carbon because it is a less electronegative atom of the polar pi bond. And the polar pi bond will break off to form a lone pair on oxygen because it is more electronegative, and this forms a larger organic molecule. And then elimination is just in reverse of that, where the lone pair on oxygen forms a double bond with carbon, forming a polar pi bond. And to avoid breaking the octet rule, the bond between carbon and chlorine breaks and becomes a lone pair on chlorine, and chlorine becomes a nucleophile.
An electrophilic addition occurs when a nonpolar pi bond approaches a strongly electron-deficient species, forming a carbocation and a bond between one of the carbons on the pi bond and the electron-deficient atom. The reverse of this is known as electrophile elimination, and is a very common elementary step because of instability and lack of octet on the carbocation. Any base present in solution will take up the proton that comes off the carbocation because a proton does not exist in its own solution. Don't forget, nature of pores, charge separation.
The next elementary step that we are going to talk about is the carbocation rearrangement. And this elementary step is very important because carbocations are extremely unstable in reactions, and they're usually intermediates in multi-step mechanisms because they are very electron deficient and unstable due to the positive charge on a carbon, making it very reactive, and it also is missing its octet. So a couple of examples of carbocation rearrangements are a 1,2 hydride shift, which uses a hydride ion, which is this H here, and it's going to move from your carbon number 2 to your positively charged carbon number 1 in order to stabilize it further. So obviously our electrons are going to move from an area of great electron density to poor electron density. So it's going to go from rich to poor here, creating a more stable product on this side. But the same is true with methyl groups can be used in a 1,2 alkyl shift. This is a 1,2 methyl shift that we have as an example here, where your methyl group here is moving from the number 2 carbon to the carbocation here, rearranging it to make a more stable product.
I'm going to talk to you about keto-eno tautomerization. Let's get started. Here we have the enolate anion. It's two resonance structures, where the first one here has a double bond between 2 carbons, and the oxygen atom holds the negative charge. Here we have the double bond between the oxygen and the carbon atom, and the carbon holds the negative charge. Carbon hates having a charge on it, which is why when we put it in solution with a strong acid, we form an enol form and a keto form. The keto form is heavily favored and is much more present in the solution because the carbon is much more willing to get rid of its charge rather than the oxygen in this case. The enol still has trace amounts, but we know that the keto is heavily favored because of its bond energy pictured over here, where its bond energy is much higher than the enol form.
So as a summary for Chapter 7, we talked about bimolecular nucleophilic substitution, which is just involving a nucleophile and a substrate. We talked about coordination and heterolysis, which is just the formation and breaking of bonds. We talked about bimolecular elimination, which happens when a multiple bond is formed in the products. We talked about nucleophilic addition and elimination, which involves a nucleophile and a polar pi bond. Then we talked about electrophilic addition and elimination, which involves an electrophile and a non-polar pi bond. And then finally we talked about carbocation rearrangements, and that's just the movement of alkyl groups bonded to carbons. And all of these elementary steps play into the larger reaction mechanisms that we'll be learning later on in future chapters. So like Stone was wondering at the beginning of our video, brownies don't just happen. You don't just go from mixed to brownies. There are a bunch of elementary steps in between to get the delicious product that is brownie.